Now we're going to learn how to do linear regression, where we fit a line, a straight line, to a set of data. In order to do this, each element of our sample, each thing in our sample needs to give us at least two numbers, so we have numerical data. And the idea is that the data points, they don't perfectly, exactly, precisely fit a straight line, but we want to find the straight line which best describes the relationship between the variables. So for instance, I want to know the relationship between the size of a house in square feet and its sales price. Bigger houses generally sell for higher prices. What's the relationship there? I want to learn the relationship between the amount of money made by a movie and its production budget, or maybe its advertising budget. See how those two things may cause the amount of money, the box office gross receipts made by the movie. I want to study, we do this oftentimes where we're studying like animals or plants, for instance, the head length and the length of a brush-tailed possum. So biologists use this a lot of time. These things are related to each other. Bigger possums are both longer overall and have longer heads, and so there's a relationship there to be found. So here's kind of what things look like. We got a bunch of data points. They're not perfectly collinear. They're not exactly on a straight line, but I want to find a line that kind of describes the relationship between these things. So I can write this as y equals mx plus b plus epsilon, where epsilon describes the randomness added to this. Sometimes we'll write this as y equals beta naught plus beta 1 times x plus epsilon. In this case, beta naught is the intercept, usually called b, and beta 1 is the slope, usually called m. So in this case, the intercept, beta naught, that's the place where that's the y value, when x equals 0, where the line crosses the y-axis. Beta 1, or m, is the slope. That's the rise over the run. That's y2 minus y1 over x2 minus x1. And the key idea here is that for every 1 unit that my x variable increases, that means my y variable will change by amount m, as long as we stay on this line. The new thing, we've probably seen that before, we've known equations of lines, that the new thing is this epsilon thing. So this is, whenever we do linear regressions, we're assuming that this is a normally distributed random variable with a mean, mu, of 0, and a standard deviation, sigma, that's non-zero. If mu was anything other than 0, we would account for that in the intercept value. So the main thing is that's just going to cause random scatter above and below the line. If it's not normally distributed, if it's some other distribution, then our standard methods of fitting a line no longer apply. So that's something to keep in your mind. So what do I want to do? How do we do this? How do we find the best possible slope, m, and the best possible intercept, b? Well, we need to consider the residuals. The residuals are the differences from the data point to the line. They're the differences in y values between the data and the linear model. So I go through my data points, like on this little graph up here. The residuals are those little green thingies. The line is blue, the data points are red. And so the residual is where I subtract the two y values, the y value from the data point, and then y hat, in this case, is the corresponding y value if you go vertically to the line. So in order to get that, we take our y value, yi, that's the actual measured y value, and then we put our x value into the linear equation. So we put x value in there, beta naught plus beta 1, xi, that sort of thing. And then that gives us the corresponding y value, and we subtract those to tell us what it is. If our data point is above the line, the residual is going to be positive. If our data point is below the line, our residual is going to be negative. So for every single data point that we're fitting, we have a residual. And so we're going to choose the slope and the intercept to make the residuals as small as possible, except that as small as possible would include negative values. I don't want lots and lots of really very negative numbers. No, I want them all to be close to 0. So to do that, what we do is we take all the residuals and we square each one of them. So when you square a negative, it becomes positive. You square a positive, it's another positive number, right? And so then we add up the sum of the squares of the residuals, and we will find the slope and the intercept that will minimize the sum of the squares of the residuals. So that's our criteria that we use to pick out the best slope and the intercept. And how do we do that? Well, we're not going to do that by hand. Computers will do that for us. But the idea behind it is there are several ways to get to the math behind it. One idea is straight out calculus. If I want to minimize something, well, I want to take the derivative of it, set the derivative equal to 0, and then solve for the value that sets that equal to 0. So that's one way we can derive the equations for finding the best slope and the intercept. We're finding the slope and the intercept that makes the sums of the squares of the sum of the squares of the residuals as small as possible. All right, so let's do a specific example. Suppose we're studying moose. Here's some real data. A biologist went out, tagged and studied 25 moose. First step, anytime we're doing any kind of linear regression here, is we need to make a plot. We need to look at the data and see that, hey, this looks like basically a straight line with some normally distributed random stuff on there. If it doesn't, if there's some curvature to it, if there's a nonlinear relationship, if there's something else going on here, I want to know about it, and that this is not the right tool. There are more complicated ways of fitting equations to data. But in this case, we're going to fit a straight line. So what we want to do is, in this case, the biologist, one thing, they measured the age of each moose and the weight of each moose. And so we want to take a look at this. So we read in the data file. We're doing a plot command here, age on the x-axis versus weight on the y-axis. Usually we choose for the x-axis, we choose the thing that is at least a potential cause factor, and we put the response variable, the potential effect factor, on the y-axis. In this case, we're thinking, yeah, maybe as moose get older, that might cause them to increase in weight, and so that's why we put the age on the x-axis, weight on the y-axis. And so we can look at this and say, okay, that's not ridiculous. This is not a relationship which is obviously nonlinear. This might possibly be fit by a straight line with some random scatter around there. So whenever we fit a straight line, fitting a straight line is easy. If you make a graph in Excel, you just right-click on the thing and bang, you can put the line in there. This is probably one of the most commonly used statistical procedures and one of the most commonly abused statistical procedures, because there's a whole set of assumptions that go into this. Every time I'm going to fit a linear model to some data, I'm assuming a whole bunch of things are true. If any of those assumptions are untrue, well, forget about it. All this goes right out the window and the line is meaningless. So the first assumption is there's underneath all of this, there really is a straight line, perfectly straight linear relationship, plus some normally distributed stuff. If you see some clear curvature to the data point, don't fit a straight line to that. That's ridiculous. Second assumption, like we said, is that the residuals are normally distributed random variable. Another assumption is that the variability of the residuals remains roughly constant. That's violated often. That's one of the most common things that people mess up, where there's a lot of big standard deviation, large variability in the middle, and then maybe it decreases as we get toward in one direction or another. And this model assumes that the standard deviation of those residuals, the variability, remains roughly constant throughout the whole range of x values. And then another big assumption is that each individual data point is independent of each other individual data point, which is the assumption behind basically everything we do. So, for example, suppose somebody says, I want to know if temperature and humidity are related to each other. So they take the data from a summer, and each day, they look up the daily temperature and the humidity, and then they make a graph of these, and we got something here, let's fit a line to that. No. You see, these are not, in that case, that would not be an independent random sample. That's a time series. The temperature and humidity on one day are going to be strongly correlated to the temperature and humidity on the next day. These things are probably similar to each other. So no, that's not an independent random sample. And so it does not make sense. There's some assumption, one of these assumptions is being violated in that case. All right, so the first thing we want to do in order to quantify this, to measure the linear relationship here, is the Pearson correlation coefficient, often just called the correlation. So this is represented by the letter R. Different textbooks and places will use a capital R or a small r. And it describes how strong of a linear relationship we've got here. R as a number, it varies between, the smallest possible number you can have is -1, and the largest possible number you can have is +1. So R is always in that range between -1 and +1. If you've got R of +1, it means you have a perfectly, exactly straight line linear relationship with a positive slope. On the other hand, if R equals -1, you got a perfectly straight line linear relationship with a negative slope. And so we can see some examples up here of what different R values look like. And so in reality, if we're studying anything, rather normal, then we almost never see +1 and -1. That's too easy. But, values of 0.8 and -0.8 and 0.4 and +0.4, those happen all the time. And notice if we have another relationship here, like that bottom row of stuff like that, there's relationships there, but it's not a straight line linear relationship. And so we get a 0 out there. 0 says there's no straight line linear relationship going on here. If we want to do this for this data set, the command is core, C-O-R. So into the R statistics program, we type core of moose age, moose weight. Again, we're putting age on the x-axis, weight on the y-axis, and we get 0.792. That looks a pretty good relationship here. All right, the next thing we can do is we can square that and get what's sometimes called the coefficient of determination, or the R-squared value. Since we square it, well, let's see, negative values squared become positive, so R-squared is strictly between 0 and 1. And one reason why we do this is it has a particularly useful interpretation. R-squared tells us the percentage of the variation in y that is accounted for, that is explained by our linear model, by the variation in x in our linear model. So in this case, let's take a look. R squared, we had r was 0.792. We square that and we get about 0.6, but basically 0.63. So that tells us that in this data set, about 63% of the variation in moose weight, my y variable, is accounted for by moose age in this linear model. And then the rest of it is not. So there's like, I don't know, 37%, the remaining is not accounted for. So that would come down to our epsilon, to our random variation sort of thing. Sometimes we will have the R-squared value, and then we'll want to have the correlation R itself. In that case, well, we take the square root, but we also need to decide whether we want the negative or the positive root. Remember, every positive number has two square roots. The square root of 4 is positive 2 and negative 2, right? So if we want to do this, we take the square root of R squared, then we need to think and say, does this line have a positive slope or a negative slope? If it has a negative slope, we just have to slap a minus sign on it. Okay, so let's run through this data. All right, so we're going to do this in R. First thing we want to do, obviously, is plot out the data. So we use the plot command, just like we did a minute ago. The next thing, I think it's really useful to show me the line on the graph so I can see what it looks like and assess whether, those residuals look like they're normally distributed or what, So R has a wonderful command for that. It's called ABLine, A-B-L-I-N-E. Now what we do is we do AB line, no open parenthesis, and then we do LM. That means linear model. Fit a linear model to this. Then we do another open parenthesis, and notice now I've got moose $weight, the weight column out of the moose data frame, and then a tilde, and then moose $age. So in this case, now notice whenever we use the tilde, we're thinking of the first thing as being the effect, and the second thing is being the cause. So now the x and the y are now reversed. This is important. It's easy to mess that up. When I just use the straight out plot command, plot moose age, comma moose weight, now it's putting age, the first thing on the x-axis, weight, the second thing on the y-axis. When I fit a linear model, I want to put the y first. It's saying this is being caused by that. So that tilde, again, that's that character in the upper left part of the keyboard there. And so when I do AB line, fit a linear model of moose weight, tilde moose age, then it adds a straight line to that, and I can see that, yeah, that's not obviously silly. That's not obviously goofy. I don't know, maybe more data, we'll see what happens, but see how that works. And then I want the details of the linear model. What is the slope? What is the intercept? We're not going to do that by hand. R does it for us. So in this case, I'm going to wrap summary around the linear model command. So I do summary, open parenthesis, LM, open parenthesis, moose weight, tilde moose age, close, and it gives me a whole bunch of stuff. All right, first thing tells you the function call, so that's fine. Then it's going to show the residuals. So again, the residuals are the differences in y values between the actual data and the line. And so the main thing we're looking at here is these should be roughly symmetrical. If they're normally distributed, normal distribution is symmetrical. It's centered on 0. And so I look at this, and are the maximum and the minimum and the first quartile and third quartile, are they kind of symmetrical? And it's like, yeah, maybe. That's not obviously silly. Maximum of 382, minimum of negative 314. They're both in the 300s-ish. Third quartile is positive 169. First quartile is negative 143. Good. Those should be roughly plus and minus of each other. The median relative to these numbers should be roughly around 0 because a normally distributed has a mean of 0. And this is not obviously silly. That's kind of what we're looking for at this point. Do I have warning signals? Do red flags go up? No, that doesn't look too bad. All right, next it gives me the coefficients. All right, so let's see. We've got 4 columns, estimate, standard error, t-value, and then probability that this is greater than t, that's a p-value. And then I have 2 rows. One is for the intercept, and one is for the coefficient of moose age. So first thing we need to know is that estimate tells me the slope and the intercept. The slope in this case is 41.305 because that's the coefficient of moose age. And then the intercept is 370.482 because that's labeled intercept. Okay, so I can read that off. So here at the top of the slide, there's my equation of my line. Y equals 41.305x plus 370.482, where x is moose age and y is moose weight. So there's the first column of it. The second column gives me the standard error. That tells me, all right, the variation in these based on this data set, these 25 moose. So that 370 has a standard error of 99. The 41.305 has a standard error of 6.63. All right, the next thing we have is the t-value. The next column is the t-value, which is a test statistic on the null hypothesis that these are 0. Suppose that there's nothing but just random variation going on here. These x values and these y values are utterly uncorrelated. They've never talked to each other. They've never interacted with each other. So that therefore my equation of my line would be y equals 0x plus 0. And so what we do is to get our test statistic, we take the estimate divided by the standard error. So 370.482 divided by 99.153 is 3.736. So this intercept is 3.7 standard deviations away from where you would expect to be if the true mean was 0. Similarly, my slope of 41.305 divided by standard error of 6.633 is 6.227. Again, this is a t-value. This is a t-test statistic that's more than 6 standard deviations away from where we would expect to be if the true value is 0, and this occurred just by random chance. So then the final column is the p-value. Probability of getting a value greater than the absolute value of this. This is a two-tailed p-value. And so the p-value on the intercept, on the testing the null hypothesis that the true intercept is 0, and anything we got different from 0 is just as a result of random variation. I get a p-value of 0.00108. That's only about 0.1%. That's nice and statistically significant. Notice we get 2 stars on that because, as the significant codes tell us, that's significant at the 0.01 level. That's less than 1%. And then on the next one, oh, good grief, that's tiny. 2.36 times 10 to the minus 6. Well, that's super duper statistically significant. We get 3 stars. That's significant at the 0.001 level. And so that's, again, that's the probability. If I just randomly chose one set of x's and then I randomly chose another set of y's and they never talk to each other or interact, they're just 2 uncorrelated lists of random numbers, what's the probability I would get a slope that far from 0? I mean, if I just randomly choose random numbers, I'm not going to get a slope of 0 by just random variation. I'll get something at least slightly different from 0. And I want to know, is 41.305 within slightly? And in this case, no, it's not. That's a test statistic of 6, the p-value of 2.36 times 10 to the minus 6. So that means this is very, very unlikely to get a slope that large if the true slope was 0. And that's kind of the most important one there. That tells me the significance of the regression. That tells me that, yes, there is a relationship here between the moose age and the moose weight. Let's dig into these just a little bit more. One more time. The slope is 41.305. That has units of, remember, slope is rise over run. It's change in y over change in x. Y, in this case, has units of pounds. X has units of years. So this is pounds per year, 41.305 pounds per year. What does that mean? Well, that means, according to this data, on average, for every extra year a moose is older, the weight should be larger by about 41.305 pounds on average from this whole data set. So therefore, if I now sample 2 moose and I find, this moose is 10 years older than the other moose, on average, I would expect the older moose to be about 413 pounds heavier than the younger moose. All right, and so again, on this, the test statistic being done here is on the null hypothesis that the slope and the intercept are equal to 0. I don't need to know the details of exactly how all this is computed. If you tell me what the null hypothesis is and what the p-value is, I can make sense out of that. I can do that. I can interpret any p-value as long as I know what the null hypothesis is. So these are both two-tailed probabilities. They're the probability of getting the value we got or something more extreme, assuming that there's no relationship here. That's the null hypothesis. The x and the y are uncorrelated with each other. And so usually what we want is the p-value associated with the slope, because I want to know, does this data establish, do we have clear evidence that the weight of a moose and its age are related to each other? The p-value says, well, what's the probability of getting data like this, assuming there's no relationship? That's super duper tiny. And so we say, well, therefore we reject the null hypothesis that our slope is statistically significant, because it's the slope that connects the x and the y value. X and y might be unrelated to each other, but if you can have a non-zero intercept, the intercept might be, I don't know, 500 pounds or whatever it is, and then as maybe x and y would be unrelated, but you could have a non-zero slope even if x and y are unrelated. unrelated. So you would have a non-zero intercept if x and y are unrelated. But if x and y are unrelated, then that tells me that the slope must be 0. All right, so let's take this, and we can also use this to make confidence intervals because they told us the standard error. They didn't tell us all the details about how to get the standard error. That's long and boring and tedious. But we can use that standard error to get whatever confidence interval we want. So let's make a confidence interval on the slope. In this case, again, the slope is 41.305 pounds per year. Standard error is 6.633 pounds per year. If I want to make a 95% confidence interval, well, that's going to be the estimate plus or minus critical t-value times the standard error. In this case, we have data from 25 moose, and now we fit 2 parameters to the data, both the slope and the intercept. So that decreases our degrees of freedom by 2 in this case. So our degrees of freedom is n minus 2. If I'm doing a simple linear regression like this, 25 minus 2 is 23. So that's how I get my critical t-value. So I go to R and I do QT of 0.975, comma 23, or negative QT of 0.025, comma 23. Both cases leaving 5%, and the tails 2.5% in the left tail, 2.5% in the right tail, 95% of the stuff in the middle. I get a t critical value of 2.07. And so if we multiply that by our standard error of 6.633, that gives me my margin of error. So the confidence interval will be 41.305 plus or minus 2.07 times 6.633, and that gives us a range from 27.6 to 55.0. This is interesting. Okay, so again, the interpretation of this is that based on this data, this sample of 25 moose, we are 95% confident that the true slope, meaning if I were to measure the whole population of all moose in this region and measure their weights and their ages and find the slope of that, we are 95% confident that the slope of the whole population will be between 27.6 and 55.0 pounds per year. That's kind of interesting. Okay, so we got 41.305. Well, you know what? Stating that 5 at the end really isn't very meaningful. The slope is somewhere between 27 and 55, probably somewhere in the 30s and 40s, but we just don't have enough data points. We only have 25 moose. That's not enough to pin this down very specifically. So we really don't know that much on exactly where the sample is, what the slope is based on this sample. We can say pretty sure that it's not 0. Notice 0 is not in that confidence interval, so we reject the null hypothesis on the null hypothesis that it's 0. But knowing that it's 41, this data can't pin it down that specifically. All right, so to summarize, we use linear regression when we get at least 2 numbers from each item in our sample. And now I want to find the equation of a perfectly straight line that relates them. The assumption is what the x's and y's are related to each other based on a perfectly straight line plus normally distributed random stuff. We choose, in order to pick out the best slope and intercept, what we do is we choose the ones that minimize the sum of the squares of the residuals. That's our criteria that we use for picking out the best slope and intercept. So anytime we do this, step 1 is always plot out the data and see, is there a clear nonlinear relationship here, meaning some curve, or yeah, okay, fair enough. Does it look like we got random stuff on top of a straight line linear relationship? We quantify this with the correlation, the Pearson correlation coefficient, which is a number between -1 and 1 that measures how strong the linear relationship is. Positive 1 is a perfectly strong, perfectly straight line positive slope. -1 would be a perfectly straight line negative slope. R² is what we get when we square that, and that is interesting because that tells us the percentage of the variation in y that is accounted for by our linear model with x in there. And when we do the linear regression on this, it is useful to test the null hypothesis that the slope is 0. So the null hypothesis says x and y are unrelated. There's no connection here. And so every time I want to fit some data, I want to say, okay, does this data at least establish that there's some relationship between x and y? And so that's probably usually the most useful hypothesis test to do in this case.